Thermochemical fluids in greenhouse farming, short TheGreefa. Welcome to the TheGreefa Training Programme, Module 1, Introduction. The consortium, a team of research institutions, SMEs, agricultural operators, and legal experts, has been formed to ensure a balanced mix of skills and expertise for developing a cost-effective and innovative technology aimed at significantly reducing the use of fossil energy in agriculture. The scope of the project involves developing and testing a cost-effective and innovative technology that will significantly reduce the use of fossil energy in agriculture. This proposed solution by TheGreefa directly aligns with the EU's key objectives to increase the use of renewable energy in agriculture, where greenhouses are becoming increasingly important. In developed countries, a high quality of life especially concerns the diet, which must be fresh, healthy, and varied. Long transport routes are often necessary, and the transport of fresh fruit and vegetables causes high CO2 emissions, contributing significantly to the food's environmental footprint. Poor regions with adverse conditions for cultivating cannot afford the import of food. For both cases, greenhouses equipped with dryers and water recovery systems represent an ideal solution, provided they meet the following criteria, which TheGreefa does. The focus of TheGreefa is on applications for greenhouses and drying processes. The greenhouse technology will include applications for climate control, including heating, cooling, and air humidity management. The proposed technology uses liquid desiccants known as thermochemical fluids, short TCF. Typical TCFs are salt solutions based on sodium hydroxide or magnesium chloride. The common effect in all applications is the hygroscopic properties of TCFs, which allow them to absorb water vapor from the air, releasing sensible heat converted from the latent heat stored in the vapor. To give you an approximation of the process, on the right-hand side of the slide, when 1 ton of air humidity is absorbed into the TCF, the energy involved with the phase change releases approximately 680 kilowatt-hour of heat. The absorbed humidity is then condensed into liquid water. The uptake of water dilutes the TCF. When the TCF is diluted to a certain degree, the process cannot continue and the TCF must be regenerated, which involves driving out the absorbed water. On the left side of the slide, the reconcentration, regeneration process is shown. The same amount of energy released during absorption, approximately 680 kilowatt-hour per ton of evaporated water, must be reintroduced into the system. Temperatures below 60 degrees Celsius are sufficient for the regeneration process. The exact temperature depends on the phase equilibrium of pressure vapor between the TCF and the ambient air. In the middle of the slide, the water leaves the TCF and can either be released as water vapor taken up by dry air or condensed and recovered as pure water. The diluted TCF can be stored and regenerated when heat is available, such as during sunny days, using solar energy, or by utilizing residual heat. The concentrated TCF can be stored in simple plastic containers, for example IBC tanks for small applications, for as long as necessary, serving as seasonal storage. The ability to shift the regeneration process in time and space compared to the effective use of TCF is a significant advantage over existing sorption processes, such as desiccant rotary wheels. In regeneration mode, the process can also be operated with a humidification and evaporative cooling effect as an additional benefit. Greenhouse heating is the most significant cost factor for greenhouse operations in Central Europe. TheGreefa can be successfully applied in these regions, reducing the energy required for heating. The application is explained in the slide, which compares the energy and water flows of a standard greenhouse on the left, with the greenhouse where the proposed technology is installed on the right. The total energy consumption, the red arrows, will be significantly reduced. On one side, there will be zero heat loss from ventilations because the air is recirculated and the humidity is removed by the TCF. On the other side, the heat is released through the absorption process. The technology consists of an open counterflow heat and mass exchanger absorber, which dehumidifies and heats or cools the air using TCF by absorption. The process is also highly sustainable for drying agricultural goods like herbs and fruits, which must be dried immediately after harvesting, regardless of weather conditions. This application is explained in the slide. The air is dried in an absorber in counterflow with a concentrated TCF, but it is not necessarily heated, as heat could harm the leaves or vegetables and affect their quality. In a closed cycle, the released dry air is then injected in the drying chamber, where it extracts humidity from the vegetables or fruits. The diluted TCF can be stored without thermal loss and regenerated when renewable heat, for example solar heat, is available again. Compared to state-of-the-art systems using compression dehumidifiers, a absorption-based dryer limits electrical energy consumption to the operation of fans and liquid pumps. The required thermal energy can be entirely provided by a low-temperature heat source, making it fully renewable. After a regeneration process, the energy provided can also be stored without any losses. After absorption, the TCF reaches a saturation point and becomes insufficient for further drying purposes. To regenerate the TCF and release the absorbed water, the process is reversed. The TCF is brought into contact with dry air, causing parts of the water in the TCF solution to evaporate into the air passing through the device. Low temperature heat is typically required to increase the air temperature and decrease its relative humidity, facilitating the process. The temperature level depends on the vapor pressure equilibrium between the air and the TCF. In any case, it will always be below 60 degrees Celsius. During this process, the heat is stored inside the TCF as thermochemical potential, also concentrated TCF. The absorption and deabsorption can occur in the same column, called the absorber, at different times. The direction of water humidity flow is determined by the vapor pressure equilibrium between the air and a TCF. The thermochemical fluids used in this project are magnesium chloride and sodium hydroxide. Magnesium chloride is used for air conditioning and humidity control in greenhouses, although it is not commonly used in drying processes due to its lower hygroscopicity compared to lithium bromide or lithium chloride. Magnesium chloride solutions can reduce the relative air humidity to above 30% at ambient temperature, which is about 20 degrees Celsius. This is sufficient for greenhouse applications, where the required humidity ranges from 40 to 70%. The advantage of magnesium chloride lies in its high availability, as it is a component of seawater with a concentration of 1 kilogram per cubic meter, and its very low cost, which is approximately 100 euros per cubic meter. Sodium hydroxide is used for drying applications, whereas magnesium chloride is not suitable for this purpose due to its low hygroscopicity. For crop drying, the air humidity needs to be reduced to approximately 10% at the absorber outlet, which is achievable using sodium hydroxide. Sodium hydroxide is also highly available and low cost. A limitation of sodium hydroxide is its reaction with CO2 in the air, but this reaction does not significantly impact the drying process because the air is recirculated in a closed-loop absorber drying chamber. Both thermochemical fluids are harmless. Magnesium chloride is a product of salt preparation for cooking, while sodium hydroxide is used in an ingredient in special bread preparation. Thank you very much for your attention. If you want to know more about thermochemical fluids in greenhouse farming, then follow our TheGreefa Training Programme with our Module 2 demonstration of the technologies. Thank you very much.